Hey, welcome to the 27th session, Flipped Classroom for Calculus. This is section 3.6, part 2, continuing with applications of differentials. We can use differentials to estimate how the function value would change when we change x. Okay? So if x is a differentiable function at x equals a, if f of x is a differentiable function at x equals a, then the change in f or y when x moves to a new value, let's say a plus some little addition or subtraction dx, is equal to dy equals f prime of a times dx. This is just the differential of y that you calculated in the first section of problems. Okay? Here's an example. Let's suppose you've got a circle. It's got a radius of 10 meters. And we're increasing the radius to 10.1 meters. And we would like to know what would be an estimate of the change in area for this circle. Now we surely could just calculate the area straightforward for each of these and then subtract them, and that would be dead on, and that would be the accurate change. But sometimes if it's a complicated function, we just want an estimate of the change. So let's try this simple one first. Area equals pi r squared. Okay, we're looking for dA. dr is the change in the radius, which is 0.1 meters, and dA would be the change in the area. So what we're going to do is we're going to take the derivative of this with respect to r. So dA dr would equal 2 pi r. So then if we just move the dr over to the other side, the differential of a would be 2 pi r times dr. Understand? Sticking in the numbers, we started at 10 meters. The differential was 0.1. So when we multiply this together, we get that the change in the area is 2 pi meters squared. This is an estimate. We can calculate the actual or the true change by actually just evaluating the area at these two values. So if you look, we've got pi times 10.1 squared. That's the bigger area, minus pi times 10 squared, the original, and we get 2.01 pi meters squared. So you can see here the estimate is quite close to the actual change. The difference between these two numbers would be what we call the error, and it would be 0.01 pi. Okay, we have some different types of change here, so see if you can follow as we go through here. There's absolute change, there's relative change, and percentage. Absolute is this is it. This is the exact change. Absolute true change is what we just did in the previous slide, where we took the area at 10.1 meters and the area at 10 meters and just subtracted them. Okay? And that's known as delta F. The estimated is what we did first on that slide, and we calculated dF, or in this case on that slide it was dA. Okay? Relative change just means, okay, take that absolute change that you just calculated and express it as a fraction over the original area. So in that case, it would be the area of the circle at 10 meters radius. Okay? And of course, if you just take the relative change, relative error, and multiply by 100, you get percent change. Okay? Estimated, take the dF that you calculated, okay, and put it over the original area at 10 meters, and that's the relative change for your estimated change. And if I just multiply that by 100, I get the percentage change. You follow? How can we apply this? Well, in the circle problem, the estimated percentage change would be 2 pi, okay, because that's what delta F would be. Okay, this is, I'm sorry, not delta F, but dF, over 100 pi, because that's the original area, and then converting that to percent multiplied by 100. You get 2%. While the true percentage change would be delta F, okay, which is 2.01 pi, divided by the original area, 100 pi, times 100 to put in percent, 2.01%. So the difference between these two percentages is we're only off by 0.01%. That's not bad. Sample problem. Let's suppose you want to calculate the depth of a well from the equation S of t equals 16t squared. You may remember that equation for an object that's dropped. All we're going to do is we're just going to drop a stone, and we're going to time how long it takes before we hear a splash in the water below. We'd like to know how sensitive will our calculations be to a 0.1 second error in measuring the time. In other words, what they're saying is, okay, how much will our total depth of the well be off if we make a 0.1 second error in measuring the time? So step one, again, this is an estimate. Step one, take the derivative. That would be ds dt, and it would equal 32t. Okay? ds then would be equal to 32t times dt. We're just moving the dt over. Apply the known value for dt. The known value is the change in time is 0.1 seconds. Step 3. Now it depends on what t is, but if we say let's let t be 2 seconds, we can calculate how much change that will make in our calculated depth. In other words, if t is 2 seconds, 32 times 2 seconds times 0.1 is 6.4 feet. This means, okay, if it took 2 seconds for this object to fall, okay, our error in distance, if there was a 0.1 second error in our time, would be 6.4 feet. Now, this error could either be in either direction. In other words, the time could have been 0.1 second too long or 0.1 second too late. So in that case, let's just say that the actual depth was 100. I could be at 106.4 or subtract 6.4 from 100. If memory serves me or my mind serves me correctly, that would be 93.6. Okay? So it just depends whether you're too long or too short. Now let's say t is 5 seconds. Well, then ds is going to be bigger because it's going to be 32 times 5 seconds times 0.1 second, or 16 feet. So the deeper the well, the bigger the actual error in footage would be. Okay, here's what I'd like you to do. I'd like you to work on the practice problems, page 314. This is the second part of 3.6, 25 through 40. Thanks, and calculus rules. See ya.